Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem of quantum mechanics. Problem having been taken from the book Quantum Mechanics Concepts and Applications by Neutron. Okay. As usual, we first come to its statement. Okay. This problem is about uncertainty principle. Okay. In the first part, we will find uncertainty in the position of a neutron, and in the second part of a person moving at slow speed. Okay. Problem statement is estimate the uncertainty in the position of part A neutron moving at 5 into 10 raised to the power 6 meter per second, and a 50 kilogram person moving at 2 meter per second. Okay, it has two parts. In the last, we have given a table from which required values will be taken. Okay, we come towards its solution. Okay, the three-dimensional form of the uncertainty relations for position and momentum can be written as delta x into delta px is equal or greater than h cut over 2. Similarly, delta x delta py is equal or greater than h cut over 2, and delta x delta pz is equal or greater than h cut over 2. Okay, this is by definition. The three-dimensional form of the uncertainty relations for the position and momentum. Here x denotes for position and p denotes momentum. Okay, the three-dimensional form of the uncertainty relations for position and momentum can be written as these three. Okay, now we take first of them. Now delta x delta px equal or greater than h reduced or h cut, where h is the Planck's constant given in the table below. This is the table, and here Planck's constant h is given. Yes, this Planck's constant is given not only in terms of joule second but also in terms of electron volt second. Okay, and by definition these uncertainties in position and momentum are given as equal or greater than h cut or h reduced divided by 2. Okay, when this is so, that is delta x delta px is equal or greater than h cut over 2, then this implies that uncertainty in position delta x will be equal or greater than h cut over 2 delta p. Okay, dear students, usually we take delta as an alternate for expressing change. Okay, so here we can assume that delta p denotes change in momentum and delta x denotes change in position. Okay, however, this expression is for uncertainty in position and momentum. Okay, when delta x delta px is equal or greater than h reduced divided by 2, then this implies that delta x will be equal or greater than h cut or h reduced divided by 2 delta p. Okay, now we come towards part A, in which we have to find out the uncertainty in the position of neutron moving at this. Okay, neutron, we know that for neutron we have various physical constants. Okay, those physical constants will be taken from this table, and further data is given in the statement that it is moving at 5 into 10 raised to the power 6 meter per second. Okay, so part A, delta x is equal or greater than h cut or h reduced divided by 2 delta p. This is equivalent to h cut or h reduced, where h is the Planck's constant divided by 2. We know that momentum is equal to mass into velocity, and here because neutron is under consideration, so we will take n as a subscript of m, that is to denote mass of the neutron. Okay, moreover velocity of neutron is given in the statement, so we will take this. Moreover, dear students, this symbol, actually dear students, this symbol is a combination of two symbols, that is one symbol equality and other symbol approximation or approximately equal to. Okay, approximately equal to is denoted by this double tilde sign. Okay, and equality is given by two such dash. Okay, so this is a combination of those two, and sometimes it is also called asymptotically equal to. Okay, in other words, it will be treated as a sign of equivalence. Okay, it also conveys the sense of equivalence, and in mathematics sometimes it also denotes congruence or isomorphism. Okay, this is quite a separate discussion. Here we have not to discuss congruence or isomorphism. Okay, but it is quite enough to explain that this symbol, that is dash and tilde combinedly written, is almost treated as equivalent to. Okay, equality plus approximation equivalent. Okay, h cut divided by 2. So here this is the value of h, which we have taken from the table which has been shown in the last part of this table of this problem. Moreover, 2 is 2, and we know that actually dear students, here in place of h cut is equal to Planck's constant divided by 2 pi. Okay, in table only value of h is given, but we are taking into consideration h cut or h reduced, which is equal to h divided by 2 pi, where 2 pi is 22 by 7 and is taken as 3.14. Okay, pi is a non-terminating, non-repeating decimal representation. It is a very special number. Okay, so value of h divided by 2 pi, 22 by 7 equal to 3.14 into this 2 into mn. Here dear students, it is important to note that here we will take this value of mn, mass, neutron mass, mn, this is 939.6 million electron volt per c square, speed of light. Okay, so dear students, this is that value, and this 10 raised to the power 6, we have eliminated million m by 10 raised to the power 6. Now this 5 into 10 raised to the power 6, this is the velocity given in the statement. Okay, we have eliminated m so that this electron volt may be cancelled with this electron volt. Okay, so next simplification, velocity of speed of light c square dot s square over meter, and we know that velocity c is 2.998, or we approximately take it as 3.0 into 10 raised to the power 8 meter per second. When it will become meter square per second square, then this second square will be cancelled with this second square, and 1 meter will be cancelled with this meter, and answer will become in meter. So after simplification, it becomes uncertainty in position equal to 6.3 into 10 raised to the power minus 15 meter, because 10 raised to the power minus 15 is equal to femto, so we can also call it as femto. Okay, 6.3 femtometer or 6.3 into 10 raised to the power minus 15 meter. Now we come towards part B. Same procedure as in part A, except the value that here we are taking this 50 kilogram mass and 2 meter per second. Okay, Here the other difference is, dear students, that in part A we have taken the value of Planck's constant h in terms of electron volt dot second, electron volt second, but in part B we are taking the value of Planck's constant h in terms of joule second. Okay, because here h is given in both patterns. Okay, so in part A one pattern and in part B other pattern. Okay, so next point is just simplification. After simplification it becomes equal to 0.527 into 10 raised to the power minus 36 meter. Yes, however here within the bracket it is written that because or since joule is equal to Newton dot meter, Newton into meter, and Newton is equal to kilogram meter per second square. So this implies that joule is equivalent to joule is equal to kilogram meter square per second square. Okay, so here we will apply this conversion factor, and after applying this conversion factor, our answer will become uncertainty in position equal to 0.527 0.5275 into 10 raised to the power minus 36 meter. Okay, this is the end of our problem. Till next video, Allah Hafiz.